Even with a perfectly calibrated concrete mixture and a highly certified nozzleman, shotcrete placement can fail. When the material hits a congested rebar cage at high velocity and ricochets backward instead of passing through, the entire system breaks down. This failure happens because of the physical arrangement of the workspace. If the physical layout restricts access or creates tight angles, good shotcrete simply cannot be placed there. This is known as the geometry trap. Shotcrete placement relies on pneumatically projecting concrete at high velocities. To achieve full compaction and encapsulate the reinforcement, the nozzleman needs a direct, unobstructed line of sight and the correct angle of approach. When physical obstructions force the nozzle to be held at an incorrect, shallow angle, the material behaves unpredictably. It will accumulate on the front face of the reinforcement rather than penetrating through and filling the receiving surface behind it. Because an unshootable geometry guarantees structural defects, the physical readiness of the site overrides the technical perfection of the mix design on paper. Moving from the mix specifications to the actual staging area requires evaluating pre-placement readiness. This readiness combines multiple variables: the receiving surface, the reinforcement layout, formwork, embedments, access routes, lighting, and the mechanical equipment. These variables operate as an interdependent system. Treating them as isolated checklist items ignores how they physically interact in the field. A failure in a single variable compromises the entire operation. A well-tied rebar cage cannot be shot properly if poor lighting obscures the work, or if restricted access prevents the nozzle from reaching the required position. The inspector's primary objective before any pumping begins is to confirm this holistic state of readiness. If the physical conditions guarantee a failure, the placement must not start. Conventional cast-in-place concrete uses enclosed formwork to contain a poured mixture. Shotcrete, however, typically relies on one-sided formwork, or no conventional forms at all, projecting material directly against an open surface. Where forms are required, they must be exceptionally rigid and heavily braced. They have to withstand the extreme energy and intense vibration generated by the high-velocity shotcrete stream striking the surface. If the impact causes a form to move, vibrate, or deflect during placement, the structural bond is broken, and the specified line and grade of the wall are lost. The geometric shape of the forms is equally critical. This cross-section comparison shows the danger of closed geometries. On the left, a narrow enclosed form forces particle flow to swirl inward. On the right, an open one-sided form allows particles to deflect out and away cleanly. As the stream enters that narrow, closed section on the left, displacement air, rebound material, and overspray have no clear escape path. They become physically trapped inside the cavity. This trapped material prevents fresh shotcrete from bonding properly. It directly causes severe structural defects inside the finished wall, leaving voids, sand pockets, and deep weak zones that compromise the entire section. Beyond the primary formwork, specific architectural and structural features heavily influence the placement. Corners, deep pockets, and embedments like pipes and steel plates introduce physical barriers. Blockouts and sleeves disrupt the open wall plane. They physically alter the nozzleman's line of sight and often restrict their ability to maintain the necessary 90-degree shooting angle against the receiving surface. This top-down view illustrates the physical mechanism of shadowing. As the vector lines representing the shotcrete stream hit the front of the embedded pipe, material builds up rapidly on the obstacle. This blocks the stream from reaching the receiving surface, carving out a sharply defined empty void zone directly behind the pipe. These embedments are usually specified by the engineering design. The inspector operates within strict boundaries and must not relocate or adjust approved embedments without formal authorization. Because the obstacles cannot simply be removed, the inspector must identify them before placement begins. These are high-risk encapsulation zones. They demand specialized shooting techniques from the nozzleman and strict, focused observation from the inspector. Executing those specialized techniques requires room to maneuver. Shotcrete hose is heavy and rigid, requiring significant physical space for the nozzleman to control it effectively. A common error is confusing worker access with placement access. Providing enough scaffold planking for a worker to stand on is entirely different from providing the volumetric space required to properly orient the nozzle at a right angle to the work. The worksite is often cluttered with physical interferences. temporary scaffold cross-bracing, stacked building materials, and equipment from other trades frequently block the required shooting position. This restricted space forces the nozzle into shallow, ineffective angles. It also prevents the assistant from controlling the whip hose and blocks the crew from clearing rebound out of the placement area. If the crew lacks the physical access to maneuver the equipment and hold the correct angle, a technically perfect, well-formed wall instantly becomes unshootable. Alignment controls guide the final dimensions of that wall. Ground wires, shooting wires, and screeds establish the required thickness and plane, and they must be correctly located and completely stable to ensure accuracy. To verify that alignment and observe the placement quality, the crew relies on environmental factors. Lighting serves as a critical active tool for quality control. Shotcrete inspection is distinct from other concrete testing because defects are primarily identified visually, in real time, at the exact moment the material strikes the wall. Inadequate lighting obscures the signs of failure. Shadowing behind rebar, improper material buildup, and poor encapsulation are impossible to see in dark environments, allowing defects to be permanently buried under fresh shotcrete. The operation itself makes this worse. The pumping process generates dust, mist, and exhaust fumes that further degrade visibility across the workspace. Without high visibility and strong lighting, real-time quality control breaks down completely, rendering the inspector blind to structural defects as they happen. To catch these geometric, access, and visibility issues before pumping begins, inspectors utilize a predictive procedure known as the mental walkdown. This process requires the inspector to start at the exact location of the first planned placement and physically trace the exact path the nozzleman will take along the wall. Walking this path raises critical spatial questions. Where will the nozzleman stand? How far does the hose reach? Where will the rebound fall? It also forces specific observational checks. Where are the geometric blind spots? Where will material build up first? Where will the inspector stand? Completing this mental exercise transforms a static checklist into a dynamic assessment. It brings immediate attention to spatial conflicts and physical barriers that two-dimensional construction drawings simply hide. In the field, this dynamic assessment often conflicts with schedule pressures. A common friction point occurs when a staging area is visibly congested, yet the crew claims they can make it work. Consider a scenario where a scaffold cross-brace blocks a tight corner. The nozzleman can reach the general area, but the brace prevents them from holding the nozzle perpendicular to that specific corner. There is a sharp difference between physically blindly spraying material toward an area and the geometric requirement for proper structural encapsulation. Spraying at an angle guarantees a void. In a second scenario, a conventional form closes off the back of a narrow structural section. As the material enters, displacement air and rebound have no way to escape, guaranteeing weak zones in the concrete. In a third scenario, a placement is scheduled for the early morning in deep shadows, with only a single backlight behind the nozzleman. The receiving surface is completely obscured, destroying the possibility of visual quality control. Firmly, the rule is absolute. No amount of manual effort or high-quality material can overcome a physical geometry or environmental condition that prevents proper placement. To manage these risks systematically, inspectors use a standardized 4-question inspection framework to evaluate pre-placement readiness. This flowchart models the logical loop. Question 1 asks, "What should I see?" This defines the baseline expectation, confirming that the site requires stable forms, clear spatial access, and adequate lighting. Question 2 asks, "What am I actually seeing?" This requires identifying real-world deviations from that baseline, pointing out blocked corners, shadowed embedments, or inadequate lighting setups. Question 3 asks, "Why does it matter?" This forces an immediate assessment of the structural risk, evaluating exactly how the poor geometry or lack of visibility will prevent proper placement. Question 4 asks, "What action is required?" This determines the corrective protocol. The issue must be resolved or the project's approved disposition process followed before any pumping begins. Applying this 4-step loop ensures the inspector does not act as a passive observer, but operates as an active risk manager, stopping failures before they are permanently cast in concrete. To summarize this lesson on readiness, first, formwork must be exceptionally rigid, heavily braced, and geometrically open enough to allow material to escape. Second, architectural embedments and temporary works act as physical barriers. They create hidden blind spots and introduce severe encapsulation risks. Third, successful placement relies on human execution. Both the crew and the inspector require unhindered physical access and high visibility to observe and control the quality of the work. Your final field takeaway is straightforward. Before you formally approve a site for readiness, stand directly in the footprint where the nozzle man will work and ask yourself, can this area actually be shot correctly? With the physical geometry validated and the site fully ready, we will transition to inspecting the material itself. Next lesson, materials, mix properties, and inspector checks.